about limits and it's about limit and continuity, and then later on we'll study about differentiability too. Starting off with limit. So if we have a function, say f from some domain, some range, say, and we need to find the limit of this function. What's the limit of a function? It's basically, if you look at it graphically, because it's more intuitive when you look at the graph. We've already seen this in the case of sequences. So this is a point, then the limit of the function at this point is basically when x tends to a from either of the directions, where does your f tend at that point? So where does x tends to something a, where does your f go? That's your limit, right? The conditions to calculate limit, like if you need to find the limit of, we're not discussing the definition, we're just trying to get at what is needed to calculate the limit or to even talk about the limit of a function at a point a. If a is the point, first thing that you need is, and that's the only thing that you need basically, you need this thing to be in the domain. Now what is this thing? You need this set to be in the domain. This is domain. This is basically an interval. It could be as small as you can think of. It could be a very small interval, but we need an interval around A, which is contained in D. So we need something around A to be contained in the domain. Otherwise, we cannot talk about the limit of a function around A. We want this interval. Now, epsilon could be anything greater than 0. You can take it whatever you want, but this thing for some epsilon should be contained in the domain. Is this clear? This is like the very basic thing that you need to know. Am I audible?
Yes, ma'am.
Yes,
But
ma'am.
who defines
Yes, ma'am.
who defines D?
D is the domain of the function. This is, if you've been given a function, let's just say
Okay.
this is a function. Graphically, you do understand what limit of this function at x is equals to a means, right? It just means when your x
Okay.
tends to a, where does your f go? That's what it means. And intuitively or graphically, it's easier to see from here. What you want, now how you define it is, as we've seen it here, if you want the limit at a, you want a domain around a. Otherwise, it's like this. You want to approach to a. It's like this. A is on the x-axis, right? So you want to approach to a. So you would need this thing, some interval around it to be in the domain. Otherwise, how would you? You can't just jump from here, right?
Okay.
If you're here and you're approaching to a, you can't suddenly jump from here to here. You need an interval around a to tend to a. So for you to tend, for x to approach a, you need an interval around a. So all in all, the condition to calculate limit is, if you want to calculate limit,
Is this a doubt session?
no, it's a summary session. Limit of f at x equals a.
Can I ask doubt?
Yeah, towards the end of the session, we'll take up doubts. So you can ask them. Is that okay? So if you want to calculate the limit of a function at x equals to a, what you want is, the condition is that your, yes.
Ma'am, when will be the quiz 2 revision session, ma'am?
Calendar for that. Around, it's in August, I guess. The beginning of August.
Okay, ma'am.
Ma'am, your voice is not very clear. It's a little bit going up and down.
It's actually your voice is a little lower actually.
It's buffering.
Okay,
ma'am.
is it
Yes,
fine
ma'am.
now? Is it better now?
Yes.
Okay. So if you want to calculate the limit of a function at a point, say x equals to a, we're not talking about what exactly limit is. We just first need to know what's the condition to even talk about limit of a function at x equals to a. So first thing is, you don't need a to be in the domain. Now this is not the condition. Even if your a is not in the domain, you can calculate the limit at x equals to a. That's one interesting thing. And the other thing is, you don't need a to be in the domain, but you need an interval around a. By what I mean by interval around a is, even if a is not there, let's just say we don't have a, but we have this thing in the domain, it works fine. Then you can calculate limit of a function at the point a. So for example, when you take fx equals to 1 by x, so graphically you know what limit is, right? So this is 1 by x, and let's just take the domain to be r positive. This is the domain that you're taking. Now r positive does not have 0. 0 does not belong to r positive, but you still can calculate the limit of this function 1 by x at x equals 0. When x tends to 0, you can calculate the limit of this, which in this case would turn out to be infinite, right? So you can calculate the limit even if the point is not in the domain, but you would need a neighborhood in the domain. Now, look at this. There is this, if you take 0 to 1, say. So 0 to 1, 0 excluded and 1 included is actually in the domain. So to calculate limit at a particular point, you need a neighborhood around that point. To be by neighborhood, we mean an interval. We don't need that point to be in the domain. We just need something around it, something of interval form to be in the domain. That's one thing. And what exactly is limit? It's simply fx. So L is called the limit of f when x tends to a, say. This means that your fx tends to L when your x tends to a. And when we say x tends to a, so there are two possible directions to approach a. If your a is on the x-axis, you can either approach it from here or you can approach it from here. So we denote these directions by this. This means this direction. You're approaching x from the positive side. And this means you're approaching x from the negative side. Here. This one is called the left hand limit and this one is called the right. No, this one's right hand. So, and for your limit to be defined, for this limit to be L, you would want fx extending to a from the positive side and extending to a from the negative side, both to be equal to L. That's all. Is this part clear till this?
Yes, ma'am.
Yes, ma'am.
Okay. So we just see what are some of the possible the functions that we studied so far. So first we'll take up, let's just take sin x. So a sin x's graph looks like this. Graphically, you can do it. And so if you'll approach to any point, not just 0, if you'll approach to say this point, then your y will approach to this height, right? So your sin x, when x tends to a, is simply just sin a. That happens with a lot of other functions too. Same happens with e to the power x, because it's like this, right? Same happens with log x. It's like this. But if you take the limit e to the power x when x tends to, say, let's just say when your x tends to minus infinity, this is it. So if your x tends to minus infinity, that means your y keeps decreasing. Can you see that your y keeps decreasing as your x tends to minus infinity? Yeah. This limit is 0. No one's responding from the classes. If there's any doubt, you can ask it.
Sure, ma'am. We're getting it.
Yes, ma'am.
This is it. And if you take ex as x tends to infinity, this will be infinity. If your x goes to infinity, your y also goes to infinity. It keeps increasing. Here you have the log x. We're just having a look at it graphically. We're trying to figure out what limit is graphically, and that's what you basically do. But all the other points, it's just to take this thing where a is not 0. This is just log of a. And if you take log x when your x tends to 0, from the positive side, note that you can only approach x from the x equals 0 is this thing, right? You can only approach x equals to 0 from this side, the positive side. So this x tending to 0 minus won't even make sense. This is
Minus infinity.
minus infinity. Yes. And then we have polynomials. So if we have anything, let's just say any polynomial in general.
Excuse me, ma'am.
Yes.
Ma'am, somewhere we understand the basic function like e raised to the power x log x, but when it comes together now, and then we have to find number of solution in some question as PYQ is also given. Uh, we I don't able to solve such question. Can you please help?
Are those questions from this week?
Sorry, ma'am.
Are the questions that you're talking about from this week?
No, ma'am. It's a PYQ question. I actually don't know, but concepts are from this week.
This is a summary session. We'll just get done with the summary quickly and then we'll take the doubts at the end. Is that okay?
Okay, ma'am.
Okay. This is the general polynomial thing here. So it's basically when you calculate the limit at any point, it's just this thing. Okay. The next thing that we have is continuity. Limits, were not going into the very detail of it because they've already done limits at a lot of places till now. We can take up other examples in continuity only because continuity actually requires limit to exist. So in case of continuity, when do we say that a function f is continuous at x equals a if this is your definition of continuity. So what you want is if your x is approaching to a, you want your fx to approach to fa. Or this is one thing, or you can just say, now here's, when we talk about continuity, we don't actually want we don't want this interval or any interval for that matter. We had one condition in limit thing that we'd want an interval around a, even if a is not in the domain, we would want an interval around a to be in the domain. That's not a condition in continuity. So you don't want an interval around a to be in the domain. Instead, you want a to be in the domain. Now, a should be in the domain. Why? Because you want the value at f equal. You want the value of f at a. So you want a in the domain. In limit, you didn't want a in the domain. You wanted this thing to be true. In continuity, you don't want this thing. You want this thing to be true. So even if either you say this, or if this is the case when we have two cases in continuity. First case is when your x can actually approach to a. That is when your a minus epsilon and a plus epsilon is in the domain. That's one case when you talk about continuity. And the other one is even if your a minus epsilon, a plus epsilon is not in the domain, then you can just simply say that, let's just say that this is a function. Then this function is actually considered continuous because that's how we're defining continuity. This function would be considered continuous. Even if you can't approach now, these things, these points here are not in the domain. Can you see why these points are not in the domain? Okay. So this is a function. This point is in the domain. This is in the domain. These points are in the domain and the other points are not even in the domain. So, but this function is still considered continuous. You can't approach this point, x equals to, let's just say this is x equals to a. You can't approach this point, but this is still considered a continuous function. That's how we define the continuous function. So either here in the definition, either you would want if your a minus epsilon, if a minus epsilon and a plus epsilon is in the domain for some epsilon. Is it very confusing? I just want to know if that it's clear.
Yes, ma'am, it's
Yes, ma'am, it's clear.
Okay.
Yes, ma'am, not confusing.
Okay.
Uh,
So
Ma'am, can you
Ma'am,
explain
but
that graph you explained
this one.
for the continuous function, continuity?
This one, right? So
Yes.
we have not yet defined continuity. So what continuity is, either you would want, this is your domain, right? Your x-axis, something on your x-axis would be in the domain, right? So you would want, either you would want this thing, an interval sort of thing. So if you want to check the continuity at A, so either you want your A minus epsilon and A plus epsilon to be in the domain. That's, if this thing is in the domain, then the continuity f would be continuous at A if your fx tends to fa when x tends to A. If this thing holds, then continuity means this. But if this doesn't hold, let's just say that there's a point here, separately, B point. You've defined the function like this, and then at B you've defined it to be this. Then this is considered to be continuous here as well, by definition only. That's the definition. So if you're A, what does this mean? If you have B here, this means there is no epsilon, no neighborhood of B such that B minus epsilon, B plus epsilon is in the domain, right? Do you agree?
Yes.
Ma'am, what is
It is-
epsilon?
Epsilon could be anything. Like if you have a A here, this is A minus epsilon, A plus epsilon. It's just used to denote an interval around A. That's
It is
Okay.
basically a set of values, right?
set of
So
what?
we
And
need
it
Set
is
of
just like
values,
The
like
only constraint on epsilon is you need epsilon to be greater than 0. That's
How's B continuous? I mean, how is it continuous at B?
because that's how we define a continuous function. That's the definition of a continuous function.
ma'am, but what if my graph can go towards negative y-axis? Then it is not necessary for the epsilon to be less than, I mean, greater than z.
Oh no, this just means when you take an interval around A, how do I take it? By this, we just want to say that we need an interval around A which is contained in the domain. That's what we want to say. So if I want an interval around A, what would I do? I take A minus something and A plus something. Isn't it?
Okay, ma'am, got it.
That's it. So we're putting a constraint over epsilon that your epsilon is greater than 0 to make sure that this goes on the positive side and this goes on the negative side. That's it.
so, ma'am.
Can you
Here,
say-
this epsilon is just like h which we take in limit h tends to 0.
Yes, you don't have to get into the detail of that. I just wanted to say that there has to be an interval around A, this thing. Around either you need an interval around A to be contained in the domain, or you want, for limit, you need an interval. So I hope this part is clear that to calculate limit at a point A, you need an interval around A. Even if A is not in the domain, you need an interval around it to be in the domain, right? I hope this
Okay.
part is clear.
Yes, ma'am.
But I
But
just
for-
want to understand, ma'am, is B part of the domain? Is it in the domain?
Yes, it is. If you've
Okay.
defined the function here, it's in the domain, right?
Okay.
So if this is your function, let's just say, so this is the domain, right? And then let's just say I define this to be here. Then this is also in the domain. So this union, this B is in the domain, right? So by definition, either you would want all in all, I think it's gotten a little confusing here. Either you want this thing to be in the domain, then this condition should hold. So if a neighborhood around A is in the domain, you'd want this thing to hold. Otherwise, if there is no neighborhood around B, like in this case, around B there is no neighborhood that is contained in the domain. In that case, we consider F by default to be continuous at B. Is that okay?
Yes,
Yes.
ma'am.
Basically, in this interval, there are infinite points, right?
Yes, there are in every interval other than this. If you consider this, other than this, every interval has infinite number of points.
Excuse me, ma'am, please explain the last thing again.
Okay, let me just define what continuity actually means, then it will be clear. So for F to be continuous, either if, let's just say, continuity at x equals to A. So if A is in, if A minus epsilon, A plus epsilon, this is a little complicated. We just mean an interval around A. Interval around A is in the domain, then you'd want this. Fx tends to Fa when x tends to A. Okay. And if your A minus epsilon and A plus epsilon is not in the domain for any epsilon. Now, what does this, in simple language, this just means there is no, as in this case, there is no interval around B which is contained in the domain, right? The domain is this, and then just B. So, no interval around A is contained in but A should be in domain. In both these cases, A should be in the domain. You can't skip this condition. You can have a choice here. In the interval around A, you can have a choice, but A should be in the domain for continuity. Then F is continuous at A. Now you can ask if there's any doubt in the definition. Is there any doubt in the definition?
No, ma'am.
Ma'am.
So let's just do some examples. Let us just take up e to the power x again. And let's just say that we want the limit at, we just saw that the limit at, now there's one more thing to it. You can't talk about continuity at infinity because infinity is not a point. So this is not even a concept. You don't talk about continuity at infinity. You just talk about continuity at a point, a finite point, which is in the domain, right? So if you take, say, A, then this will be e to the power A. I hope everyone knows why this is true. No one has a problem with this.
No.
Which is the same as, so this is the same as this thing. Limit extending to A.
Ma'am,
Yes.
if a function is a convergent, then we can say it is defined at infinity.
Function, we don't
Sorry,
use the
ma'am,
term
if its
convergence for F.
continuity is defined at infinity.
Continuity, that's what I'm saying. Continuity is a concept which is not talked about at the point infinity. We only talk about
Even
continuity at finite points.
okay,
Because
ma'am.
infinity is not a point, no, it's where is infinity on real line? Let's just say this is infinity. This is a real line. This is the real line.
Okay,
Where's
ma'am.
infinity here? Infinity is more of a concept, it's not a point. So that's why we don't talk about continuity there. And graphically, if you look at it, it just, so intuitively what we think, what comes to our mind when we think of continuity is that it's a function that we can draw without lifting our pen, right? Like this one. You don't need to lift your pen while drawing this. And a discontinuous function likely looks like this. Like you need to lift your pen here. At this point, it's discontinuous, right? And we just, okay. So are there any other examples, particularly in your head, that you can come up with that we can discuss here to discuss the concept of continuity? Can you think of any functions? The functions whose continuity you would want to discuss here?
A situation where there is a open point.
In the domain?
Um,
In the
yes.
function curve.
Ma'am, do you want us to give examples of cases?
No, I
Continuous
just,
function.
if you have anything that you would want to discuss the continuity of, you don't have to give the examples of continuous functions. You can just give example of anything and we'll discuss the continuity of that function here.
Log function.
Just like a modulus function, which turn
Like
sharply.
1 by x.
Okay, one by one.
Greatest integer function.
Okay, greatest integer function is this, right? We just draw it. We know how we draw it. This point is not included. It's included here. This is how it looks, right? I just forget about the negative part. It looks like it's not continuous. Anywhere, if you see a graph of function and it obviously looks like it's a discontinuous function, you have to lift your pen. Then it is a discontinuous function, because what's happening is, but that's not how you should check if a function is continuous. What you do is you check the limit. Let's just say you want to check the continuity at this point. I mean, I know that almost everyone would know that this function is continuous at this point. Let's just say this is they're extending to a, and a is not an integer, right? It's not an integer. So x, limit of your greatest integer function, it's this, right? The greatest integer function is this only. When you'd approach to this point from here, you'll have the function's value approaching to this right? So it's this only. In the case when you take a to be a non-integer, it's this. And when you take it from the negative side, from this side and from this side, it's the same. You reach the same point. That means, you reach the same height you reach, right? So you get both of these to be a, this thing. It's continuous at this.
And basically, if the right hand limit and left hand limit
Yeah.
will be same, then we can say it's a continuous function.
No, it's right hand limit, left hand limit should be same. And both of them should be equal to the value of the function at that.
Okay.
That's what we discussed here, no, in the definition. This. The limit extending to a plus, limit extending to a minus should be equal to fa. This is for limit. This part you need for limit, right? This is what you mean when you say that the limit of f as x tends to a is, say, fa or L or whatever. So you would need, until this point, it's the definition of limit. And then if you take everything, it's the definition of a continuous function. Is that okay?
Yes. Ma'am, so if we take 3 as 3 number 3 to check if it is if the greatest integer function is continuous at 3, so it will not be continuous. Am I right?
Yep, it's not continuous, because from here, if you see, let's just say this is 1, this is 2, and this is 2. And from here, you will see that there's a, graphically, you can check that there is a gap here, right? You'll have to lift your pen. That's the graphical logic. And then if you look at this, if you approach to this 3 from the left hand side, you'll get this, right? The limit of fx would be this point, right? And
Yes,
if you
ma'am.
approach it from here, it will be this. So both of them are different. So in this case, even forget about the continuity, the limit does not exist, right?
Yes, ma'am.
Does not exist.
So this is same for a seal function.
Sorry, what?
Is this same for a seal function?
I can't hear you. It's
No. Is the condition applicable same for a seal function?
what function?
Seal.
Just,
I think he said math dot
oh,
C.
ceiling function. All right.
Yeah.
Yeah, it's the same for ceiling function. Ceiling function is not continuous at integers. Floor function is not continuous at so both ceiling and floor functions are not continuous at integers because they have a significant jump from here to here. Okay. So should I pick examples on my own, or do you want to discuss any particular examples that are
Ma'am,
in your mind? Yes.
Ma'am,
can you please
actually,
discuss about?
uh,
Yes,
can
ma'am.
I?
Yes.
Ma'am, if anybody don't have problem, please discuss the number of solution type question.
We're not, this is a summary session, and if this is related to this week 8 thing, we can discuss it here because we're summarizing week 8. We'll take the doubts at the end if there are any from other weeks.
No, ma'am, you are asking now na ki, that we should solve some practice or example on.
No, what are you trying to get at? What are you trying to
Ma'am,
say?
no, ma'am. Now you
Ma'am,
just asked to all of the student what type of question discuss now. That's why I asked again.
So, ma'am, uh, can you
No,
please
no.
discuss about
In the
10x graph?
10x,
Yes, ma'am. That is a similar means somehow similar to this because that is also breaking at some points.
tan x, do you mean tan x?
Yes, ma'am.
This one?
10x. Yes, ma'am.
Okay. So tan x is, if you look at a graph of tan x, it's somewhat like this, right? It looks like this, right?
Yes, ma'am.
A lot of people might not know it. We'll do it the definition way as well. You can't always, it's better if you know the graph of the trigonometric functions than the basic e to the power x log x and all. So this is it. If you will take the continuity of it, let's just say this is 0 and this is pi by 2, right? So you take the interval of things that at pi by 2, there's a significant discontinuity at pi by 2 and all the odd multiples of pi by 2, right? If you take any odd like this one, this is an odd multiple, then this is an odd multiple again. So the problem is that the limit tends to infinity. As your x tends to pi by 2, say, the limit of tan x tends to infinity. This is infinity. It's actually, okay, let's just have a look at this thing. Do you think tan pi by 2 is a defined thing? We've already discussed that we only talk about continuity at points where your function is defined, right?
we not define on
Yes, ma'am.
infinity.
So is it defined on pi by 2? Do you think there's a finite value for tan pi by 2?
No.
We don't talk about it there. Is that all right?
Yes. Ma'am,
Yes.
Elsewhere it's
can we
continuous.
Ma'am, can we say tan x is equal to sin x upon cos x?
Yes, that's
As sin x and cos x both are continuous functions, so we can say the tan x is a continuous function.
okay. We'll get at the algebra of continuity in a while. So then we'll take up this thing. Okay. When we'll come to the rules for it, then we'll take up this example and we'll discuss why this is not a continuous function at pi by 2. All right. And
Okay, ma'am.
So, ma'am, this graph is continuous at minus pi by 2 to pi by 2 means at that fixed domain, but it is not continuous.
yeah, it's continuous here. These 2 points are not included. Is that okay?
Yes, ma'am.
Okay, and continuity at a point, and then we talk about continuity of a function. So continuity of a function just means we say that a function is continuous in general if it is continuous at every point in the domain. I think we don't need to write that, right? So we'll just move on to the
And
rules
what?
then.
Can you repeat?
So when you say the one that we've discussed is continuity of f at x equals a, right? So we've discussed the continuity of f at a point. And then there's continuity of f in general. So we say f is continuous if it is continuous at every point in the domain. If f is
Okay.
continuous for all x belonging to the domain, then we say that it's a continuous function. Now we'll discuss the rules. We can say,
Excuse me, ma'am.
yes,
Ma'am, I have posted a question in the chat. Can you please discuss it?
which one?
Ma'am, I have typed it in the chat.
Is it this one?
Yes, ma'am.
Yes, ma'am.
Okay, we're discussing continuity for one variable functions. Why are we having two variables here? I don't think we're discussing the continuity of functions in two variables.
Ma'am, can't I consider it as a function, as two functions in one variable, but just a multiplication of them is given?
No, you can't. It must be something else. Is it something like this? Or maybe fxy product?
Ma'am, it was f of x comma y.
We've just started with the definition of continuity in one variable. And we're not even done with the rules yet. You have a question from continuity of functions in two variables. Let's just do it. But in your syllabus in week 8, it's only do you have functions of two variables in your syllabus in math 1?
No, ma'am.
Ma'am, this
Then
question
why
was
are
in
we,
one of the PYQ.
okay,
No, actually,
now
in the
let's see
last
why.
PYQs, I think week 9 was also there. But week 9 and week 8 were combined equally.
If this is a function question from week 9, I don't think this is the place to discuss it now.
Okay, ma'am.
We can discuss it towards the end if that's okay. Because
Okay,
it's
ma'am.
not in week 8. Okay, so the rules for continuity. This is first one. So firstly, you would need f and g to be continuous. So f and g are continuous. Then we say that your f plus g is continuous as well. And your f minus g is continuous. F g is continuous and f by g is continuous provided your g. So let's just say if you're discussing the continuity at A, then your g should not be 0 at that point. Or if you're discussing the continuity in general on a domain, then your gx should not be 0 anywhere. So wherever you're discussing the continuity, your g should not be 0 there. So if your f and g are continuous, all of these are continuous. And this is continuous too. Multiplication with a scalar where c is in. And then we have, so I don't think we need to do the examples for this. So there was one thing about tan x. So your tan x is sin x by cos x. And here we use this condition. So your cos x should not be 0, where you want to calculate or where you want to find the continuity of this thing. If you want to check the continuity, say x equals to something, then at that point your cos should not be 0. I hope that answers the question that someone asked a while ago. Someone had a doubt in this thing. Why it's not continuous at pi by 2 when sin x and cos x are continuous at pi by 2. Because your cos x is 0 at pi by 2. That's why this thing is not continuous. Okay. Then we have sandwich principle, which you've already done in limits. It says, let's just say you have 3 functions. And if the limit of this function and this function at a is say L, then the limit of fx at a is x is L as well. So let's just say this thing. And so for your x between 0 to 1, your x square is less than x, right? So this is it. So you have 1 by x and 1 by x square. Supposedly, that let's just say, now for this you'll need your x. You want this thing. You know that your x is, let's just say, you're taking the domain to be r plus. So for your x to be in r plus, this is true, right? And let's just say that this thing, we know that this thing goes to 0. And this is also going to 0. So this thing also goes to 0. That's how your sandwich principle works.
How did you get 1 by x in the middle?
This one.
Yeah.
So we're considering x to be a positive real number. Otherwise, this is not true. First thing is this. All right. This is only true when x is a positive real number. And then for a positive real number, your x square is, so the thing is, when you
But
take the
for
limit as x tends to 0, I forgot to mention this. If you're taking your x to be tending to 0, this is, but calculating the limit when your x tends to 0. So in this interval, you basically want to know what happens when your x tends to 0. So you're interested when your x is very close to 0. That's where you're interested. That's why we are considering the case x square less than x. So for x in 0, 1, your x square is less than x. And for x greater than 1, your x square is greater than x. But we're not interested in this part. Why? Because your x is tending to 0. So you will be in this interval mostly. Or eventually you're going to be in this interval, right?
Okay.
So your x square is going to be less than x for all x in R plus. So 1 by x is going to be less than 1 by x. And obviously both of these are positive, so this is going to be greater than 0. Is this okay? Is this clear?
Yes.
We're
Yes.
considering
When you do 1
but
by
if
1
if
by
like okay, you go ahead.
sorry. I was just thinking if you do a 1 by, then shouldn't all the inequalities change? It should reverse, right?
we reversed it, right? We reversed this thing. How do you? We're not reversing this. We've left this alone. We reverse these two. You can't reverse this. Otherwise,
Okay.
it would
But
just mean less than infinity. If you
even if we
reverse all
don't
of this,
reverse,
yes,
the 1 by x and 1 by x square are coming undefined, but infinity, but the 0 is staying 0.
what is your question? I don't think I understand.
I mean, if we put limit x tends to 0, then the 0 stays 0. 1 by x goes to infinity, and 1 by x square also goes to infinity.
Okay, we're not, yeah, I think we just took the wrong example then. Let's just take this to infinity then.
We can do
Let's
1.
take,
Limit x
let's
tends
just
to
take
1.
the limit to infinity. That's fine.
Okay.
It works just fine. If you take 1, you'll get a 1 here and a 0 here. Then you won't be able to apply the sandwich rule.
Yes.
That's the problem. So even for that, I mean, then you'll have to make some changes here, I think. Because now we're not considering x to be in 0, 1. So if you take this thing, so you'll have this is, in fact, this doesn't hold then. If you're taking the limit to be, if you're taking this thing, then your 1 by x is here and 1 by x square is, this is it, right? For x greater than 1. This is true for x greater than 1. So if you want to approach infinity, you should consider this thing. Previously, we considered this thing because you were taking the limit to be x tending to 0. So near 0, this is true. But when your x is, when you're tending to infinity, then your x is greater than 1, right? Eventually, if your x is tending to infinity, eventually your x becomes greater than 1, right? So this is the inequality to consider then. Otherwise, if x is tending to 0, you should consider this one. Is that okay?
Okay. Okay.
Okay. So this thing is going to 0. And this thing is going to 0 as well, that means. Because this is obviously a constant function going to 0.
Yeah.
Excuse me, ma'am.
Yes.
Ma'am, the x square should be greater than x na for x greater than 1.
Yes.
Then, ma'am, why this on the board you have written like this?
This one,
Is this a special condition? Can you please lower the slide?
this.
Yes,
This
yes,
one is
ma'am.
for x belonging to 0, 1. When your x is in 0, 1, this goes.
Oh, okay, ma'am.
So if you take the limit tending to 0, in that case, you should use this thing. Because if you're approaching to 0, basically your x is in 0, 1 interval. Eventually means ultimately you are in this interval. If your limit is tending to 0.
Okay, ma'am. Thank you.
Okay. So next up, taking the differentiability thing. What does differentiability means? Differentiability and derivatives basically. So basically we've done we've just discussed the conditions to discuss the continuity of f at a point and to discuss the limit of f at a point. So can someone just repeat what we've discussed, the conditions to discuss the continuity of a function at x equals a, and the condition to discuss the continuity of the function at x equals to a.
Limit x tends to a negative equals to limit x tends to a positive equals to limit x tends to a of and of x, then we say that the function is continuous.
Yeah, but there's a condition on a, right? So if you want to find the continuity at a, what's the condition on a?
It should be in
Yeah.
interval a plus epsilon and a minus epsilon.
Okay, for continuity and for limit.
It should also be in the domain.
Should also be in the domain.
It should be in the domain, and it's okay if a minus epsilon, a plus epsilon is not in the domain. We discussed that even if you're a, we discussed this, right? In this case, when you take
Yes,
discrete points, this is considered to be a continuous function. You don't, because is there a doubt? We've discussed this in very detail, and I see your
No,
guys are
ma'am, no
still
doubt.
confused about it.
Excuse me, ma'am.
Yes.
Ma'am, no doubt, but I just general question. Whenever we ask for continuity to check, we just if the expression is given, and we just go to the check and LHL equal right hand limit, na left hand limit equal right hand limit.
Okay.
This should be approach or the other thing we should approach.
Which other thing? Are you talking about continuity?
Yes, ma'am.
What about for continuity? Would want the left hand limit, right hand limit at a point to be equal to this. That's the definition of the of continuity at a point.
Yes,
What's your
ma'am.
doubt?
Ma'am, when my doubt is when the graphs are given.
Okay. Let's just say you've been
Uh,
given this graph. What's your doubt now?
on the graphs, different graphs are given like so then how we check the continuity on such graphs
Okay,
if
let's
we
just we
don't know
just discuss the
expression?
if you don't know what.
Expression is not given, only the
Okay,
four
so the
graphs are
expression is not
given.
given. Let's just say you don't know what the expression of this thing is. We're not even using the expression here. But you can you see that this function won't be continuous at this point? We don't know what this point is, but it's not continuous here. Because the left hand limit is this, the right hand limit is this, and this. And they're not same. So in this case, your left hand limit and right hand limit are not same. So your function is not continuous here. And let's just say you have this thing. You have this function, and then you lift your pen for a bit. You define the function's value at this point to be this, and before this, it's this. So let's just forget this. Just have this thing. Then let's just define your function to be this. This is, let's just say we don't know what this, we're not using the function here. We know that this function is this 1 by x when your x is not equals to 0 and 0 when your x is equals to 0. That's how this is one point on the graph and then this is the graph. Let's just say we're not making use of this. We're not doing it the definition way. We'll do it the graph way. So at this point, the function's value at say, this is 0, we already know. So the function's value at 0 is 0. But the limit, this limit is infinity. So from right hand side, you have this limit. From left hand side, you have, or even this is minus infinity. So in this case,
But f of 0 shouldn't be defined, right?
it's not defined according to this, but we've defined it this way. We can, this is a function, right?
Okay.
It's a function. You can define the function on your own too.
Okay.
I've defined the function to be 0 at x equals to 0. 1 by x is not defined at 0, but I have defined it to be 0.
Okay.
This is not 1 by x. This whole function is not 1 by x. And even if you take it to be this, so in this case, your left hand limit and right hand limit both are infinity. But you can't define your function's value to be infinity because that's not a number. So if you define it to be 0 or any finite number, that's what you can define. When you define a function, you give it a finite value, right? You can't give it infinity value.
Okay.
So this function is not continuous because although the left hand limit and right hand limit are same, but the function at 0 is not, you can't, this is it. It's 0 here. Even if you define it to be something else, it's still not continuous. Because you'll have to define it a finite number only.
Ma'am,
Is that clear? Yes.
ma'am, this point is clear. My another doubt is, can I ask?
Yes.
Ma'am, like somewhere we are given a curves in the graph, a big curve. Two different curves are given which are not intersecting, but they are like parallel seeming to us. Can you please draw?
What is it?
Just ma'am, randomly draw two graphs which can be seen.
Okay. This one graph, and what's the condition on the other graph?
Uh,
They don't intersect.
no, ma'am, they are not intersecting.
Okay. Let's just have this one.
Okay, yes, ma'am. And ma'am, but it's just a point given. Sometime a circle is given and point is given. How we are gonna check continuity?
Continuity of which you at a
Yes, ma'am.
given in, yes.
Hi, yes, we are given intervals. You can take value as your choice, ma'am.
Let's just take this interval.
Uh,
So what's the question? What do you want to do in this question?
ma'am, can we check continuity if the interval is given on between these two graphs?
So continuity you will be checking of f, right? Let's just say this is f, this is g. So you will be checking the, if you don't need two graphs to be here unless you're taking the sum of it or you're taking the product of it. Then is when you need the graph of both of them. Otherwise, if you just need to discuss the continuity of f, you can just see and tell that this function is continuous. You won't be given a graph whose continuity, if you will have to check graphically, you won't be given a function whose continuity you cannot tell by just looking at it. So you will be given a graph whose continuity you will be able to tell by just looking at it.
Okay, ma'am.
This function is continuous, right? If you're talking about continuity in this interval, then this function is continuous in this interval. In fact, it's continuous everywhere. Let's just say you have this thing and you take this thing. So in this interval, the function is still continuous because the discontinuity comes here. And it's not a part of this interval. So the function is continuous in this interval, but it's not continuous. F is not, if this is F, then it's not continuous everywhere on R, but it's continuous on this interval. Is that all right?
Okay, ma'am. Somewhere my doubt is clear. Thank you so much, ma'am.
No problem. Now we're discussing the derivatives. So for derivatives, for continuity, this condition is essential and this condition is not essential. Essential means if it's true, then well and good. But if it's not, you don't need it. It can be true, not be true. We've discussed in the definition of continuity. And here, if it's not in the domain, this is, so the important condition, the necessary condition here is this. This should be in the domain. This condition can be dropped. Even if it's not true, it's fine. So these conditions are not important to check the continuity and limit respectively, but these are. The first ones are. Is that okay? Okay.
Yes, ma'am.
Let's just move to differentiability. So similarly, we talk about the conditions for differentiability at A. At x equals to a, if you have to discuss the differentiability of a function. So you need it to be both So now you need both of the conditions, and we'll just discuss why you need both of the conditions. You need this to be true, and you need this to be true as well. To discuss the differentiability of a function, say f at x equals to a, you need both these conditions to be true. And let's just see what differentiability is. So by definition, we say that at x equals to a function is differentiable if this is basically a plus h minus a, which just turns out to be this thing. So you can simply write it as this, h tending to, wait, this is h tending to 0. If this is a finite thing, then we say that your function is differentiable at a, right? This is the definition of differentiability. Does anyone have a doubt in this part? There shouldn't be, because we've not discussed anything so far. We've just discussed that, and now we'll discuss why we want these to be true. So the definition is this only. Yes.
Ma'am,
There
can you
should be a
please
zero plus minus.
What?
Ma'am, can you
There are
please tell
doubts.
exact things of finite? Does you mean by exact value, like natural or any integer value or any real value?
H. Okay. You're talking about H, right?
No, ma'am.
So,
H I understood, but the finite you are saying, the finite
okay.
value, then it is
Finite
differentiable.
means not equals to infinity. That's what it means. So, like any finite number, it could be a rational number. All you want is a real number here. I hope you know that infinity is not a real number.
Yes,
So
ma'am.
Yes,
we
ma'am.
want a real number here. That's it. By finite, I mean not equal to infinity. So if you're getting the limit equal to infinity, then this function is not considered to be differentiable. Is that okay?
Further, what is the third condition?
Third condition, that's okay. This is it. And there are only two conditions too.
Okay.
These are the conditions too. Let me just write it. So this is, see, the definition is this, right? The definition is just this part. So what are these two things then? This is, let's just say we are discussing limit here. So to calculate the limit of this is a function, this is something, right? And you need to find the limit of this thing at when h tends to 0. So we've already discussed to find the limit of a function at, let's just say this is fh or a plus h, because a is constant, so it doesn't matter. If you need to find the limit of this, you need, what do you need? Your a, you want this thing your to be in the domain, right? So you basically what you need is, if you need to find the derivative at a, you need a plus h is what? Your h is tending to 0. So this is a. So this is a plus, let's just say a plus 1, a plus 0.9, a plus 0.8, and so on. So you keep coming closer to this, right? So for this to be, you want your function to be defined at a plus all the a plus h when your h is tending to 0. That means you want this thing, a, this thing to be in the domain, right? Is it clear, or should I just go into the detail of it?
I'm clear.
It's clear, ma'am.
Yes, sir, clear.
So you want your a plus h. The thing is, you want so you want your a plus h to be in the domain. That just means that you want there are two conditions here, right? This is, so you want this thing to be true. So you want an interval basically. Let's just say you don't have an interval around A which is contained in the domain. And how can you have this thing in the domain? It's not possible, right? Just look at it as a sequence. Let's just say this is a sequence. And it's if Hn is going to 0, your A plus Hn is going to A. Right? That's what you want. So you want A plus Hn sequence to be in the domain. If you want this is A, where Hn is tending to 0. Hn, if you're, that means this is the sequence. A plus H1, A plus H2, A plus H3, A plus H4, and so on. So you keep coming closer to A. Right? So you want this thing to be in the domain. And if your domain is not an interval around A, or if an interval around A is not in the domain, then do you think that a sequence would be in the domain? A sequence that tends to A can it be in the domain if this thing is not in the domain? If some interval around A is not in the domain, then do you think a sequence that tends to A can be in the domain?
No, ma'am.
That's why you need your function. That's why you need this condition. So you need an interval around A to be in the domain because otherwise there's no sequence that tends to A, right? And you want it here. Consider this as a sequence that tends to A when H tends to 0, right? Is it clear?
Yes.
Okay. So to talk about this, these are the conditions to talk about. So if these two conditions do not hold, if these two do not hold, then you do not talk about differentiability at that point. Is that okay?
Yes, ma'am.
And if these two conditions hold, then we can discuss the differentiability at the point A. Now it can be differentiable or it can't be differentiable. If this holds, then it is differentiable. Then if it doesn't hold, it's not differentiable. But to talk about the differentiability, you would need these two conditions to be satisfied. Just the way we did in continuity and limit. Is that okay?
Yes.
Okay. And then what does this value actually give you? So it's basically limit change in y by change in x, right? When your change in x tends to 0. So we are trying to discuss what this means in physical world. So this is your limit, right? And this is your y. This is y, right? So this is change in y, and this is change in x. And then you take the limit of change in x. H is change in x. A plus h minus a. So this is nothing but change in y by change in x and the limit of change in x tending to 0, which you can call as limit of, so rate of change in y with respect to x. When change in x tends to 0. This is rate of change of y with respect to x. Do you agree? I hope you know that this is rate of change of x, y with respect to x. What is that? It's, let's just say if your change in y is this, then your change in x is this, your change in y is this. And rate of change of y with respect to x simply means the rate of the change in y when the change in x is 1, right?
Yes, ma'am.
So when change in x is x2 minus x1, this is the thing. So if your change in x is 1, then this will be y2 minus y1 by x2 minus x1, right? So if you change x by 1 unit, your y will change by this unit. That's what your rate of change of y with respect to x means, right?
Yes, ma'am.
Okay. let's just consider a real life example. Let's just say that you have this time interval at 10 and 10 p.m. Let's just say 10 p.m. and 11 p.m. And then you have 10:30 somewhere in between. And let's just say the distance here is 0 and distance here is say 100. So when you calculate the speed, what you do is, that's the average speed, right? So it's basically 100 by 1 hour. So it's 100 kilometer per hour. This is kilometers. But this is the average speed, right? So average speed means that at a given instant, let's just say that I need to find the limit at 10:30. That doesn't mean that the speed at 10:30 was 100 kilometer per hour. It just means that it could be 60 kilometer per hour here. It's just the average speed. Like when you take the average of marks of students in a given class, it doesn't mean that every student has got 100 marks. It just means that the average is, that's what this is. So this doesn't give you the accurate picture because it's the time interval is too long and you're calculating the speed at 10:30 according to this interval. So if you shorten this interval, let's just say if I take 10:15 to 10:45, and then here we have 10:30. You get a better idea, isn't it? So if you shorten this time interval, you will get a better idea of what the exact speed was at 10:30 as compared to this one. Do you agree? Is this fine?
Yes.
And if you make it even shorter, let's just say this is 10:30 and you will do 10:31 and 10:29. So if you keep approaching to this thing, let's just say next time you make it 10:29 and 59 seconds, and this one you make 10:30 and 1 second. So you're so close to this point. That means if you will use this thing, if you will take the distance at this point and at this time, and then you subtract it, d2 minus d1, and then this thing, this time, you'll get more accurate speed at this point, isn't it?
Yes, ma'am.
Yes.
That's what we are doing in the derivatives thing. What we do here is we take f of a plus h minus f of a. This is h, but it's basically a plus h minus a only. The final coordinate minus initial x coordinate. And then you take this thing small. Note that this thing is basically rate of change of y with respect to x, which basically means this is the change in y when your change in x is 1. But what is this limit then? It gives you instantaneous change at, say, if you're at a. Change at a. Just as in this one. So if you want the instantaneous change at this point, you should keep making the interval smaller, right? That's what we are doing here. So this is this interval a plus h minus a, and you're making it smaller. Yeah. You're making the interval smaller, a plus h minus. Each time you take h to be smaller, this interval reduces. Is that okay?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
If anybody has a doubt in this, it was just conceptual. Even if you don't understand this part, it's fine. But just to have an idea of how this works in real life, it's important to know this thing. It's basically this limit gives you instantaneous change. So it's instantaneous rate of change, basically. Instantaneous rate of change at A. Is that all right? Instantaneous basically means that when you're very, very close to this thing, to the point. Let's just, in this case, your A is 10:30. So when you're very close to your point, that's when you mean instantaneous. And if you look at it graphically, it's just this. If this is your A, FA point, and if this is your A plus H, FA plus H point, And this is basically what you're doing here is, so one thing to keep in mind is the change in x. This is basically change in y. When your change in x is 1, this quantity is change in y when your change in x is 1 unit. So if you keep getting closer to this point, let's just say you're here, and then next time you take h to be smaller, so you get closer to this thing, and then closer to this thing again. So each time you keep getting closer, and you get the instantaneous rate of change here at a, at this point. Is that okay?
Yes.
Okay, so let's just discuss some examples on differentiability then. That's why we actually discuss differentiability and derivatives. That's why we discuss it, to study the change or the rate of change. That's why we've discussed all of this. And graphically, if you look at it, it's not always the case, but for simple things and simple curves, if you see a sharp curve, sharp edge in your graph, that means your function is not differentiable. That's what it means. If you want to see the graphical thing of it. Okay. So let's just take up some examples to discuss it. Let's just start with x, the very basic thing. So we know that if this is your fx, this is basically x. Let's just say that you want to discuss the differentiability at a. One more thing. So we say that the derivative exists if this is a finite number, and that finite number we represent by this thing. We denote that finite number by f dash a, and it's called the derivative of f at a. It's just representation, nothing to understand. So if you have this thing, then let's just say that you want to discuss the differentiability at a. So this is x plus a plus h minus a divided by h when your h tends to 0. So this is h by h, which gives you 1. So your f dash a is 1. This gives you f. The finite number that you get from here is the derivative of that function at a. So f dash a is 1. Another example is, let's just take up x squared this time. So you'll have, or let's just take up x to the power n directly. That will cover all x square, x cube, and everything. Let's just take x to the power n. This will give you x. So at x equals to a, to check the differentiability of x equals to a, you have x plus a to the power n minus, no, h plus a, right? This thing is, have you heard of binomial expansion for this?
Yes, ma'am. Yes, ma'am.
We're going to use that here. Or there is other way to do it as well. That's by induction. So either you can solve this, you can prove this by induction. You can, the derivative of this is, we denote derivative by dash, right? So this is n x to the power n minus 1. We'll just prove how that's true. Either you can do it by this way, or you can by using binomial expansion, or you can do it by induction. We'll do it by binomial here. So it's nc0 a to the power n h to the power 0 plus nc1 a to the power n minus 1 h to the power 1, and so on ncn and then you'll divide this whole expression by h. We don't have an h here, so we'll get this thing, right? And this is, we have an h here, so we'll get this thing cancel, and everywhere else the power of h is from here. From the third term, you have power of h greater than 2. So each time you divide it by h, you'll get h here. So you'll be left with at least one h. After this term, if you divide it by h, you'll be left with h and something n, c, k, k to the power n minus k, and h to the power k. So if this tends to 0, this whole thing is going to 0. So this is not needed here. And then you have this thing. Is there something wrong?
Yes.
Okay, so we didn't take that part, right? We forgot this a to the power n. It's this is a plus h to the power n, and this is an, h tending to 0. We forgot this. And then you have minus a to the power n. So this is this exact term here divided by h. Then you have this thing, which will give you this. H gets cancelled here. And for the other, from third term onwards, because the powers of h are greater than 2, from third terms onwards, so you will have an h remaining here. So this will, so when you will take h tending to 0, this whole thing will become 0. Yeah, from here. So you're only left with this thing, and this thing. And this is going to 0. And this is by minus an by h plus n c1 an minus 1, which is equal to 0 plus n c n minus 1. So this is your derivatives. X to the power n's derivative is basically n x n minus 1. Then next up, we'll discuss the differentiability of mod x. So mod x, if you look at, you get, let's just say you differentiability at a, so it will be a plus h. It's differentiable at a point which is not equals to 0. Because if you take anything here, you'll get this thing. This just leads to, so if your a is positive, then a plus h is positive as well, because your h you take to be greater than 0. So this is a plus h minus a by h, which will give you 0. And then if you have a plus h, even if your a is negative, you'll get minus a plus h minus minus a, so you'll get the same thing. Wait, you don't get a 0 here, you get a 1 here. This is it. Either way, you'll get a 1. Then your a is not 0. So if your a is 0, you'll get 0 plus h minus 0 by h tending to 0. And you have to take limits from both sides. So if you're taking the limit from the positive side, you'll get h minus 0 by h. And if you take the limit to be from the negative side, you'll get minus h minus 0 by h. This will give you minus 1. This will give you 1. So your left hand limit, this left hand limit of this expression, fa plus h minus fa by h, and right hand limit are not same. That's why the derivative does not exist for this one.
Why does it
0.
become minus h on
Just
the left hand side of 0?
Does not exist. So on left hand side, the mod x, let's just say this is 0. So if you have something negative, let's just say you have minus 1, then the mod of it is 1, right? So if you're considering x to be minus 1, then the mod of x is minus of x, right?
Yes.
So if your h is negative, then mod of h should be minus h, right?
Okay.
So for this function, your derivative is not, and you can see it from the graph as well. It's a sharp edge here. That's why this is not differentiable. Then we'll take up one more example.
Excuse me, ma'am.
Yes.
Ma'am, can you please explain the point of again minus 1, the minus h by h, that point? I don't get that.
So your mod x is basically x when your x is greater than 0, and minus x when your x is less than 0, right? That's how you define it. You can take 0 to be any term. That's what we've done here. So if you're approaching 0 from the negative side, that means you're approaching your h is here, right? H can take these values. So
Ma'am,
it's negative.
wouldn't x be x whether it's x is above 0 or below 0? Because it's mod.
When you have minus 2, say, and you take the mod of it, you get 2, right? So if your x is minus 2, then your mod x is not minus 2, right? It changes to minus of minus 2.
Yeah, it becomes plus 2, right?
Yeah. Which means it's minus of minus 2. That's why we take a negative here. Is this clear now?
Okay.
Ma'am, here this mod function graph is continuous, but its derivative is not existing.
Yes.
It's the thing. And ma'am, one more thing is that if we can see on graph that tangent of that graph is not possible at any point, then we can say that its derivative is not existing at that point also.
Yeah, you can say that, but for that you need to define tangents. So we'll get to that point in maybe 5 minutes. We'll discuss tangents and all in 5 minutes. And then when you have, we're short on time, so we're not taking more examples now. As you can just try to check that this function looks like this, right? So this function is not differentiable. Just try it on your own using the definition, not differentiable at integers. And
Excuse me, ma'am.
one important note here is, just 1 second. So if your function is differentiable, let's just say f is differentiable. This implies your f is continuous. Now, what does this tell us? If you see a function which is not continuous, as in this case, your greatest integer function is not continuous at integers, right? So if f is not continuous at x equals to a, this implies f is not differentiable at x equals to a. So every differentiable function is continuous, and it's the converse of this is not true. Yes, someone was saying
Yes, ma'am.
something.
Ma'am,
Oh.
what is the difference in continuity and differentiability?
For that, I need to ask, what do you find similar in these two? The different concepts. So do you see any similarity? Continuity means if you look graphically, it means that there are no breaks. But functions, there are exceptions to it, like this one, where you have breaks, but it is still continuous. It's basically, for continuity, it's this condition. Limit of a function should be equal to its value at a. By limit, we mean the left-hand limit and right-hand limit. Then that's when we say that the limit exists, right? If we have not already made it a point, then just make a point here that your limit fx, when we say that limit fx extends to a is fl, then we mean that your fx when x tends to a minus and fx when x tends to a from the positive side, both are L. So left hand limit and right hand limit both should be L. That's when we say that your limit exists and is equal to x, to L. This one. So your continuity is this, whereas your differentiability is this thing.
Okay,
If
ma'am.
this limit exists and is equal to this, then we say that it's a continuous function. And if this limit exists and is a finite number, this thing, you can just have, if A confuses you, you can just have, but we're taking A so that you don't confuse. The variable here is H. A is kept constant. That's why we're not taking X. X is generally associated with variables. So if this limit exists and is finite, by finite we mean it belongs to real numbers, then we say that it is differentiable. And its derivative is this limit at point A. Is that okay?
Okay, ma'am.
Yes.
Okay. Next up, we can discuss a function where, so we've already discussed a function which is not continuous and hence it's not differentiable either. Right? We discussed this function. We have not seen how that works for greatest integer function. That's for you to try. And if you're not able to, we can discuss that in the next class. And then we'll discuss if a function is continuous and it's still not differentiable. Continuous and not differentiable. So one of them is mod x, obviously this one. It's continuous, but it's not differentiable. And the other one is x to the power 1 by 2. So when you look at this function, you'll have square root of a plus h minus square root of a by h. We are doing it quickly. If there's any doubt in any step, you can ask. This gives you h by h as h tends to 0. This is 1 by this thing, right? So this is your derivative of this function at a point. But if you'll take your a to be, let's just say if I take a to be 0 here, then you'll have square root of h minus 0 by h. And you can't actually take it from the negative side. So
Ma'am, can you just explain what you did in the last? Yeah, I mean here.
this one,
No, ma'am, that you have already raised. That's what I wanted to know.
okay. So if you want to check the differentiability at x equals to 0, it's you can't actually, because it's, if you, this thing is not differentiable at x equals to 0 because it's not even, it's not defined here. It's on the negative part, it's not defined. So you can't take the limit here. So we should actually then, and if you even take this, you we can take only one limit then, right? Limit h tending to 0 plus. The point is, should we discuss the continuity at the end points of a function, because this is the end point of your graph. If you'll only take the limit from here, which is, that's only possible in this case, so you'll have the same thing, but then you'll have a square root of h minus 0 by h, right? So you'll have 1 by square root of h. What you'll have, and when you take the limit to be this, you'll have infinity. So we've already discussed this, that we don't want this limit to be infinity, we want it to be finite. Better example in this, what I was trying to make a point here. I was trying to give you an example for a particular case. Let's just take x to the power 1 by 3 then. If you take this function, you'll have so let's just not do it in the graphical way. We don't have much time left. It looks like this. So if you look at this, this is the tangent at point 0. So if you try to test the differentiability of it at x equals to 0, it's not differentiable here because this thing becomes infinity. That's why we don't take that here. So when you, in terms of this, what you want is a function is said to be like differentiable if you can draw this tangent here. And it shouldn't be this one. This is also a tangent, but it's x. The slope of this one will be infinity. That's the problem. That's all. If you try to find it out, we're not discussing it here, but it's because we're short on time. So this is going to be at 0. If you try to find it out, it will be infinity. It's not differentiable here. Yes.
Can you just tell me how can we determine whether a function is differentiable or not just by looking at the graph?
Okay, just by looking at the graph, the first thing is you don't want sharp turns here. Sharp edges shouldn't be there. So
Now, what if
anytime,
one side of the turn is a parabola, the other is a straight line?
this one,
Yeah, like this. Exactly.
it's not actually differentiable. And if you try to test it, you can just try to, if you want to confirm it, you can just make a thing here, x for x less than 0 and x square for x greater than 0. And then you can test this thing. It's most likely not differentiable because it will be something like this. So it's not differentiable here.
Okay. And now what are the condition?
Sorry, what?
Is there any other condition?
No, I don't think so. And other than that, this is one of the conditions where we said that your tangent should not be parallel to y-axis. So it shouldn't be a straight line like this. That's one of the conditions. This graph actually, if you look at this one, it's a smooth graph. Smooth in the sense that it's not taking any there are no sharp turns there. But it's still not differentiable at this point because the tangent here is parallel to y-axis. That's one of the other conditions that you can
But
check.
how can we know just by looking at the graph that the tangent here will be parallel to y-axis or not?
If this is your graph, then what do you think is the tangent is? Do you know how to draw tangents?
Yeah, tangent is the
You
dy
won't be
by
asked.
dx of the function at that point.
Graphically, it's this thing which gives you the direction of we've discussed it several times in class. So here at this point, your tangent is this because this is giving the direction. This is giving the direction of the flow at this point.
Yes, ma'am.
So it's parallel to y-axis, and you wouldn't be asked vague questions where you won't be able, where you are confused that if your tangent is this or it's a straight line or what is it. You won't be asked questions like that.
Now, what if the graph is not passing the point where the differentiability is asked?
So the graph has to point. If it's not passing, when we started with the topic of differentiability, we discussed that even to talk about differentiability, you need the point to be in the domain. So this should be in the domain. So if your function doesn't pass through this point, then you can't talk about differentiability here. They won't ask it. And we start with the topic of tangents. I think we've discussed tangents a lot of times. It's this thing. Let's just say this. It gives you the direction of your graph at this point. This is your tangent. It's a line basically, right? So how do you find the equation of this line? Let's just say this is y is equals to fx graph. How do you find the equation of this tangent line? So how do you find the equation of a line that passes through, let's just say a comma b, and it has a slope m? Does anyone want to answer this?
Ma'am, y minus y naught equal to m bracket x minus x naught.
It passes through this point, so it should be this.
Yeah.
This is it, right? So you already have the passing point. So if you want to find the tangent at say a comma fa, right? This is the point on the graph, a comma fa. So if you want to find the tangent at this point, you'll have y minus fa, the slope, and then x minus a, right? So we just need to find this thing. And what is this thing? This is basically, so when you just extend it, there are several ways to define tangent. So one of them is to define slope. One of them is basically what you say, or change in y by change in x thing, right? Which is the derivative at that point. So it's basically this you can take at f dash a. How do we claim this thing? If you have a comma fa here, and you need to find the slope here. So what you do is you take this point and this point, and then you join these 2 points. Let's just draw a clear graph. So if you have this curve, say, and you want the tangent, equate the tangent at this point. So you take this, let's just say this is a comma fa, and then you take two points here on either sides, and you join these two. And then you come closer to this point, and then you join these 2 points. And then you come closer. So when you will be very close to this point, when these 2 points will be very close to this point, it will be a straight line passing through just a comma fa. So all these are passing through 2 points each time, right? But when you will come very close to this point, it will just pass through this point. Is that clear?
Yes, ma'am. Ma'am, can you take some example and like some example, and then we can solve this?
Yeah, sure. But we're just trying to find what is this thing to derive the equation of the tangent at a given point. So it's basically this thing, y minus fa equals the slope, which is f dash a, x minus a. This is it, which gives you y is equals to fa. You can just solve for y and put it here. So this gives you the tangent at this point. Let's just say this is a comma fa. So equation of this line, this thing is actually this equation of this line. Is that fine?
Ma'am, what is written in the last line? Can you just read it once?
This one?
Yes, ma'am. Yes, ma'am.
It's y equals fa plus f dash a into x
Okay.
minus b. This is the equation of the tangent line at the point a comma fa. That's how you find the tangents. You know that this is the passing point, and you know the slope of it is f dash a. F dash a,
Yes,
which is the derivative of f at a, gives you the slope of the function at point a. Is that okay?
Yes, ma'am.
Okay.
Excuse me, ma'am.
Yes.
Ma'am, if a tangent has a slope infinity, then should we say that it's not differentiable?
Tangent has a, yes, that's what we discussed, right? This is a tangent, and then the slope of what is the slope of this? It's infinity, right? It's not
Yes, not
differentiable
different.
there. Not differentiable there.
Ma'am, but like y is equals to x cube has the tangent x equals to 0 and it also has the infinity.
Y is equals to x cube is this, and the tangent is this. So the slope is not. It's the slope is 0 here.
Oh, okay, ma'am. Sorry.
Okay,
Ma'am, can you take my doubt now?
we're still not done with the theory of this summary of everything. It's
So I have to wait,
let me
ma'am.
just. Yes, you have to.
Or
And
will we
this
be
is
able to
so.
complete
If you
maximum today?
sorry, what?
The maximum related to limits.
Can't hear you.
Now I'm saying, will we be able to complete the maximum today related to limits? There's a question reader assignment related to that.
We're not. I don't think there's time left today. So, and
Okay.
there's a, lots of things remaining. And one thing to note here is that when you, this is the equation of tangent in general, but when you take, let's just say, at if you have this thing, let's just say you have this thing. So your slope here is infinity, right? So you can't put it here, you can't do those things here. So what you do instead here is, when your slope is infinity, you just take x equals to 0. So your x equals to 0 is y-axis. This is that line that we were talking about here. So when you take x to the power 1 by 3, you get your slope equals infinity, and this is the tangent. X equals to 0 is the tangent at 0. So this formula won't work when your slope is infinity. When this thing is infinity, this is not going to work. This formula gives you the tangent to a given point, but it won't work when your slope is infinity. Doesn't work. So a, if you see that your tangent is parallel to y-axis, then this is not going to work there. It's just simply x equals to 0. Only works when your slope is non-infinity. Is that okay?
Yes, ma'am.
Okay. Let's just say, let's just do a small example on this one. It's if you need to find the tangent at say e to the power x at x equals to 0. So it's basically we have y is equals to fa, right? So you'll have f of 0 plus f dash 0 and then x minus 0 here. So it will be f of 0 is 1, f dash 0 is 1 again, and this is x minus 0. This gives you x plus 1. So what this means here is that at your x equals to 0, this point, the tangent is this, say if this is the tangent here, then this is y is equals to x plus 1 line. That's what it means. Is this okay?
Yes, ma'am.
Excuse me, ma'am.
Yes, ma'am,
Yes.
it is.
Excuse me, ma'am.
Yes.
Ma'am, like you take the example e raised to the power x. Can you please take mod x on graph? Very first you said it is not differentiable.
Yes.
Now if you take for this question mod y equal mod x at x equal, let's suppose to again it will show does not exist now.
No, it's just not differentiable here. The derivative exists everywhere. It's not differentiable at x equals to 0. At x not equals to 0, all values for which x is not 0, this function is differentiable.
So we can create a tangent equation on mod x.
See, if you want a tangent here, it's this line only, no? So it's basically
Not a curve.
Sorry,
Ma'am, tangent is for a smooth curve, I guess.
it is for a smooth curve, but what we mean here is that you don't even need a tangent here, because why do you actually find tangents in the first place? To find the direction. So if
Yes,
this is
ma'am.
the
It's a straight
direction,
line.
it see, wait, it doesn't mean that this, if you will take y is equals to x, you will say that this is not a smooth curve. It's a smooth curve. It's considered, you don't have to have curves like this to have a smooth curve. When we say that it shouldn't be like this, there shouldn't be sharp corners, that's all. This is a smooth curve.
Is it because the sharp curves where the point is, there's no defined tangent? Is that why it's not?
Yeah, it's because you can't, if you're at this point, you're suddenly changing the direction. You're not going here, you're not suddenly changing the direction, right? You're going in one direction, so you know where your graph is going. When you suddenly change the direction from here to here, then you don't have a tangent.
So, ma'am, for a straight line, the tangent is the line itself, no?
Yes.
And ma'am, this mod x function, only it is not defined at x equal to 0, and rest all the points it is defined, and we can find a differentiable at other points.
Wait, so you said for your straight line, your tangent is, if you take, yep, it's the line itself, actually. What were you saying?
Ma'am, I said for the mod function, only it is not differentiable at x equal to 0, and rest all other points it is differentiable.
Yes, it's differentiable everywhere else. Just use the definition for mod x. If you don't want to figure it out graphically, you can just use the definition. But if you see sharp, let's just say you're not being given the function and you're just being given the graph, then if you see something like this, it's not a differentiable. Is that okay?
Yes, ma'am. So for mod x,
Yes,
if we
ma'am.
have to find tangent like where you have pointed in the figure, I think the positive side of arm itself is the tangent.
Okay, so that when you talk about this is, are you saying that this is the tangent?
No, ma'am. Ma'am, the
So
slant line, in the slant line of the
this one,
mod x,
at this
not,
point, you do not. Okay.
yeah, not here, ma'am. Ma'am, the further if you go in the slant direction,
Here?
and yes, yeah, maybe here. So this line itself is the tangent here.
Yes, this is, if you want to find the tangent here, it's this line only. Because
Yes,
tangents
That
are just
means
meant to
every
give you directions. Yes.
yes, ma'am.
We have other doubts because the time's already almost up.
Ma'am, the last doubt in this, can I
Ma'am, I
just?
have doubt. Ma'am, me.
Okay, we can, I think we can just only take one doubt because the session can end anytime. So go
Doubt.
ahead. Yes,
Ma'am,
what's your doubt?
I shared a link before. It's from quiz practice.
Okay,
So ma'am,
Ma'am,
can you open that link?
I can open that link, but by the time I'll open it, the time would almost be over. It's already above 10. And which link is it?
Ma'am,
Because there are
yes, ma'am, ma'am.
lots of messages there.
Yes,
Okay,
ma'am.
found the link.
Ma'am, in that link, ma'am, in that link, you have to tap the Maths 1 section, and then paper, July paper, and the code is 1307.
1307.
Yes, ma'am, 1307.
Yeah, I can only see practice quiz 1, practice quiz 2. Which one are you talking about?
Ma'am, practice quiz 1.
Okay. Which one is it? The July 2025, right?
Yes, ma'am, July 2025. Then 1307 code number.
question is it?
Ma'am, question number 11 to 16.
Satellite dish is shaped like a parabola and its height above the ground in meters at a horizontal position x meters is given by this. There's a function given. An engineer places a ladder that follows the path. Wait. Okay, I can't. Can you dictate the question to me because I can't check it simultaneously and then write it.
Yes, ma'am. Okay, ma'am.
Okay,
Ma'am, a satellite dish is shaped like a parabola
okay,
and its height is above the ground in meters at horizontal position. X meters is given by fx is equals to ax square minus 12x plus 10, where a belongs to real number minus 0.
okay.
And then next paragraph is an engineer places a ladder that follows the path of line given by y is equals to 8x plus 3 at the point where x is equals to
Wait, wait,
0.
wait. Just repeat the ladder part.
Ladder that follows the path of line given by
Okay, there's a
y is
ladder.
equal
Yes.
y is equals to 8x plus 3.
Okay. Is the question done? It's the question
No,
then.
ma'am.
Okay.
At the point where x is equals to 1, the slope of a satellite dish's curve is the same as the slope of the ladder.
Okay.
Find the value of a.
This is, have a look at this function, the slope of this. What is the slope of slope is the derivative at that point. So it's basically this. Is that fine? And if
Yes,
you
ma'am.
take, let's just
Ma'am,
define it as g.
ma'am, we have to find the differentiation of fx. But in week 4, we don't know how to differentiate.
Okay.
Means
No,
teacher
no, no.
didn't tell us.
We did. No, no, we didn't have to
So
find
we
any
can, you
differentiation.
don't have to differentiate it. You can just have it from here. So if you look at this thing, the slope would be,
Ma'am, 8.
8.
Ma'am, 8.
yeah, it's 8. If you take y minus 3, it's, so it's 8 here. And then it's the same for this one. So, uh, and you, so you can't, if you can't differentiate it, then you can't even, how do you find a then? Is either you
Ma'am,
do
that's
it
the
this way,
question.
either you equate this thing to 8 at 1. So you get the value of a. For that, I'll have to go through the theory of uh, what is what else has been given till week 4, week 3, whatever this question is from.
Ma'am, I don't think anything is given around this equation, and the value of slope and the point.
Ma'am, basically, yeah, we just had to equate the two things and then A will come out to be 10.
But for that, you need to use the this thing, no? How do you find the slope of this? It's
But ma'am, I think we were taught, I'm not very sure, but I think we were taught that 2ax
yeah, that's what I
plus
was saying.
b
That must
is the
have been told
equation of.
something about the, yeah.
Yes, ma'am, we were told, I
It
think.
it should have been there in the, otherwise you won't be able to find the derivative of this thing. You won't be able to find the equation of tangent otherwise. Yeah. So
Yeah, because we were told that we have a not a fixed tangent, but a varying tangent which depends on
Yeah.
x. Yes.
It's for this thing ax square plus bx plus c. Your, I think it was there in that week as well, that it's 2ax plus b to find the slope, and then you put the value of x here to find the slope at that point. So you just do 2ax minus 12 here, and then put the value of x here, which is 1. So you get 2a minus 12 equals 8, and then solve for a. Is that okay?
Yes, ma'am.
Whoever had this doubt. Okay. Anything else?
Ma'am,
What's the
can you
syllabus for
down
quiz two?
y equal mod x that we were discussing before?
Okay.
Ma'am, can you just little down the slide? It is already written, so don't need to bug. No,
Yeah,
ma'am,
here.
not here, ma'am. Ma'am, I was just asking, the equation exist or not exist for this? It does not have curve. I understand, as you said, it is a straight line, but somewhere students say at every point there is different direction.
I don't think I understand what you're asking. Can you repeat? What is your
Ma'am,
question?
I am asking that if tangent equation does not exist for mod x, does linear equation exist?
Linear, see, mod x, you don't say that it doesn't, the tangent doesn't exist for mod x. You say that it doesn't exist at this particular point. Or you should say we shouldn't talk about tangents at this point. At sharp curves, we don't talk about tangents. It's more like that. What is your question? Linear equation, what is it? If it's a linear equation, it's this. What's your
Yes,
question
ma'am.
related to this? This does have a tangent. In fact, this itself is a tangent to itself. Because
Okay,
tangents
ma'am. Now,
basically just give you direction. That's all.
okay, the x is itself a slope.
Not slope and tangent are two different things. Let's just get into that too. When you draw a curve, whenever I draw this curve, it doesn't mean that this doesn't have tangents and it doesn't have, it's not differentiable. I do it because it's easier to explain tangents on this one. So tangent means this line is tangent, right? And slope is, let's just say you have this curve. So your tangent is this line, and your slope is the angle, the tan of the angle that this line makes with x-axis, positive x-axis. That's what the, this is. Is that all right? So these two are different things. Slope is different from tangents. In fact, if you draw a tangent at this point, the slope of this tangent and the slope of this curve at this point are same. Is that clear to everyone?
Ma'am,
Yes, ma'am.
syllabus will be from week 5 or week 1?
For quiz 2, it's from week 5
Yes,
to week 8.
yes, ma'am. Okay, thank you.
Okay.
Thank you, ma'am.
Okay.
Ma'am, so tangent is a line and slope is a tan theta of the theta that tangent
Yeah.
is making with the x-axis,
Yes. Positive x-axis. This one.
positive x-axis.
Anything else? I think it's already 10:15, so we're wrapping up the session here. Okay.
Thank you.
Bye,
Yes,
everyone.
thank you, ma'am. Thank you so much.